thanks for the introduction. So today I would like to talk about some results concerning positive index minimal hypersurfaces in Riemannian manifold. So this is strictly intertwined with some of the most outstanding results in the field in the last decade or so. And of course, I do not claim I will prove everything, but at least I would like to give you the big picture, or at least my perception of the picture we have in front of us. So this is lecture 4, and the title I've chosen is Beyond Stability. So one of the results we've seen yesterday about the interactions between stability and curvature is that if you have say an n+1 dimensional manifold of positive Ricci curvature, then you cannot have any closed stable minimal hypersurface there. That was the result by Jim Simons. Okay, so a natural question, given that we cannot get to index equal to 0, is whether we can reach index equal to 1. Okay, so the question is that we have our Riemannian manifold, say, well, in particular, well, not only, but certainly we are especially interested in the case when the Ricci curvature is positive, because we know that index 0 is obstructed in that case. And so the question is whether it contains sigma n, as usual, a closed embedded minimal hypersurface of index 1. Okay? So there's a special case to keep in mind throughout this lecture, which is the case of round spheres. So let's say that we work in the n+1 dimensional sphere with a round metric. Okay, that's a special case where Simon's theorem applies, so stable guys cannot exist. But certainly in this case, this question does have a positive answer, because we do have equatorial. So you can pick equatorial n spheres, okay? And in this case, the Jacobi operator is completely explicit, and it's in fact very simple. The spectrum is also explicit, and you can check that these guys have index equal to 1. But how about in general? And so the general answer to this question is essentially positive with a technical point. So there's the following theorem, which is actually, the way I'm phrasing it is actually the combination of two papers, both by Fernando Marquez and André Neves. So the statement is essentially the following. So let's say that we have an ambient manifold of dimension between 3 and 7. So then it contains a closed minimal hypersurface maybe let me go on in this board with index satisfying the following inequality. So let's say such that the index is less or equal than 1, which is the most important inequality, and also, of course, less or equal then the index plus the nullity. So in particular, this says that certainly for a generic metric, which is bumpy by a theorem by Brian-White, nullity is 0, so the index must be equal to 1. But certainly, there's also another special case. In particular, okay, so there's a caveat here, which is the technical assumption I wanted to make and I didn't write. So it contains a closed minimal surface provided xn plus 1 does not contain any closed one-sided hypersurface, or if you want, even minimal hypersurface. Okay, so the existent part says, let's say that you have a closed Riemannian manifold. Suppose that it does not contain any closed one-sided hypersurface. Well, then it contains a closed minimal hypersurface. We have this estimate for the index, and in particular, if Ricci of G is strictly positive, we know that the index cannot be 0, so the index of sigma is certainly equal to 1. So let me just remark that the technical assumption there that there's no closed one-sided hypersurface is implied, for instance, by saying that X is simply connected. So the topological assumption is certainly okay if X is simply connected. So that's a great theorem which relies on min-max, and I'm going to say something about it in a second. But there's a key question in when you do min-max, which is the following, namely whether you can control the topology of the minimal hypersurface that you obtain, and in general, yeah. Right. If Ricci is positive. Not in the theorem. So I was stating it in the question because somehow it comes naturally from Simon's theorem. Simon's theorem says, well, if you have Ricci positive, then you can't have any stable minimal hypersurface. So about index 1. But then the existence part in this theorem has nothing to do with positive Ricci. Okay, so positive Ricci just comes here to say that this inequality here must be an equality. Okay. So like I was saying, a problem when you do min-max is that typically it's hard to control the topology of this object here. But there's one case we do understand extremely well, which is the case when X is just a three-dimensional sphere. And so let me now restrict my attention to that case. So let's call this theorem here theorem 1. And let me now state another theorem, which is in a sense a special case of theorem 1, but where we get stronger conclusions. So this is a combination of a work of Smith and again Marcus Neves. So let's say we pick a Riemannian metric on the three-sphere with Ricci positive. So in particular, the theorem 1 says that it does contain an index 1 minimal surface, but how about the topology? Well, the point here is that in this case, we can construct a two-sphere having those properties. So there exists S2, so you can take sigma 2 minimally embedded. With index 1. And there's a second part, which says that if you have a scalar curvature bound, then actually you can get a nice area estimate for this guy here. So if on top of that, the scalar curvature of G is greater or equal than 6, and you should keep in mind that 6 is a number that comes up as the scalar curvature of the unit sphere, of the three-dimensional unit sphere. So that's why we choose this number. If the scalar curvature is greater or equal than 6, then the hypersurface in question, which I'm going to call sigma as usual, so we want to use the letter sigma here, then sigma as area bounded from above by 4 pi. And the interesting part is that, in fact, if equality, we do understand the equality case. So if the area is exactly equal to 4 pi, then we can actually prove that the three-sphere in question has to be the round sphere. Okay, but that's sort of a different story, which I don't want to get into. Okay, so now let me say something about the proof of theorem 2. Okay, let me at least give you the flavor. So let me sketch the proof of theorem 2, and let me start with giving you an idea about the existence part. So the idea here is to apply the min-max. So let me try to explain it in the simplest possible case. So as a smooth manifold, not quite a Riemannian manifold, we can of course think of the three-sphere as the unit sphere inside R4. Okay, so and we can, there's a natural sweep out of this ambient manifold, which is just gotten by taking the height function associated to the fourth coordinate. So we can define sigma t to be just equal to the set of points on the three-sphere, such that x4 is equal to t. Okay, so we get nice two-dimensional surfaces apart from the north and the south pole, where you have a degeneration. And now we do the following thing. We look at the set of diffeomorphisms of S3, which are isotopic to the identity. Okay, so we have a preferred diffeomorphism, which is the identity, and then we have this space here a priori has several connected components. We just look at those elements that are connected to the identity by an isotopy, and we look at correspondingly, we look at the set of maps, say, phi from -1, 1 to diff 0, S3. So these are just paths in this connected component. And given an element, so we can call pi this class of isotopy. And so we can do the following. We can consider the class lambda bar made of all those sweep outs which are obtained by taking for any time t just phi at time t applied to sigma t. So we start with this very regular sweep out here, and then we consider all deformations, like all sweep outs that are gotten by deforming the initial sweep out in some reasonable fashion. Okay? So if you take the identity, well, you get sigma t again. But if you start taking diffeomorphisms that move points, you will get something more complicated. And now you compute the following number, which is called the width of the tree manifold in metric G. So this is nothing but the infimum as you let sigma t bar vary in the family of sweepouts lambda bar of the supremum, which is in fact the maximum for t between -1 and 1 of the area of sigma t bar. Okay, so for any given sweepout, you look at the largest surface that you need to go through the sphere, and then you try to optimize over the sweepout, okay? And so what we know is that the isoperimetric inequality implies that that number is strictly positive. It cannot be 0, no matter the Riemannian metric that you put on the tree-sphere. And then there's some machinery called Almegren-Pitts theory that implies, as a black box, that this number here is achieved. So this is achieved, meaning that we can obtain it as somehow a formal linear combination of minimal surfaces. So in particular, we can write W S3 G naught as a formal sum like M, let's say M1 area of sigma 1 plus MK area of sigma k, where each of these guys here is a closed minimal surface. And of course, I'm always tacitly assuming that the surfaces we talk about are embedded, okay? But then, as a third step, the remark is that if we are working with a parameter sweep out, which is this case, and the Ricci curvature is strictly positive, then in fact you cannot have anything more than one summand. So in fact k must be equal to 1 and m1 must be equal to 1, which is nothing but saying that W S3 G naught is in fact achieved as the area of a closed minimal surface. Okay, and in fact one can prove that if you start with a sweep out like that, where any non-degenerate surface is a sphere, then you can perform the whole Almegren-Pitts machinery so that sigma is also a sphere. So that's just a very rough sketch. Now, what I want to prove with some care is that if you have this scalar curvature bound, then you can actually control the area of sigma in an optimal way, okay? So notice that this bound here, for instance, certainly saturated in the tree sphere. So if you take the tree sphere with the round metric, then this procedure will give an equator whose area is exactly equal to 4 pi. So now let me prove the second part. And so for this part, like I said, I will give a detailed argument. So the statement here, let me phrase it again, is that any, so this is not about min-max, so any two-sphere inside S3G minimal satisfies area less than 4 pi, provided the scalar curvature of the metric in question is greater or equal than 6. And so the proof here is based on a very important trick in geometry, which is called Hersch trick, and I expect actually Ilana Fraser to talk about it next week as well, because it's quite important in studying some basic properties of Steklov eigenvalues. So let me show you how this works. So this is a trick that goes back at least to the 70s. So the way it works is the following. Let's take our minimal two-sphere inside S3 with some Riemannian metric. So we take phi prime, a first Jacobi eigenfunction for sigma. Okay, we know that we can take it to be positive, and without loss of generality, let's say that its L2 norm is equal to 1. Okay. So the picture is now the following. So we have this two-sphere sigma, which lives in an abstract tree manifold. Okay. So sigma lives inside S3 with some Riemannian metric G. Now there's as a standard application of the uniformization theorem by Riemann. Okay, there's a conformal map from such sigma, which has a strange metric, like a potato-shaped metric. Okay, maybe I want to call it capital phi. There's some conformal map from such sphere to the two-dimensional round sphere. So the fact that the diffeomorphism is conformal is just a statement that if you pull back the round metric, you get some positive function omega square times G. And now this sphere here lives in a natural fashion inside R3. Okay? So in particular, we want to play with the coordinate functions. So here we'll have a tree of functions. So here we have the real line, and here we have three functions, which are just x1, x2, and x3. Okay, so now what I claim, so I will put the claim in a box, then we use it, and then we get back and prove it. So the claim is that there exists an element, say F, in the conformal group of the two-sphere with the round metric, which is a group we understand very well, such that the functions Fi, which are defined by the evaluation of the coordinate functions on F precomposed with phi, are all L2 orthogonal to F1. So these satisfy, they are such that for any I between 1 and 3, phi 1 times Fi is equal to 0. For I between 1, 2, and 3. So let me explain the geometric picture. Okay, so what's going on? We have an abstract two-sphere, which is only characterized by the property of being minimal in a three-sphere with a Riemannian metric. We have this map phi that goes to S2. Now, S2 has an automorphism group, which is the conformal group. So if we apply it, we get back to S2 with a round metric. Okay, we are just moving points. So it makes sense to consider this composition. So it's a map from sigma to S2. But now S2 here lives in R3, so I can precompose it with the coordinate functions. So these are legitimate, the FIs are legitimate functions from sigma to R. Okay? And I claim, which we'll prove in a second, that indeed I can choose the automorphism so that these three functions are L2 orthogonal to the first eigenfunction for the Jacobi operator. So why is this magic? Well, let's give the claim for granted, and let's see how the area estimate is obtained. So first of all, let's recall that given that the index is equal to 1, which is what I'm assuming, sorry, here there's a magic word which I forgot. So this is about index equal to 1, okay? So we don't care whether it's obtained by min-max or not, but we want is a statement about index 1, okay, sorry. So index equal to 1 implies that lambda 2 is greater or equal than 0, right? But now lambda 2 is obtained as a variational characterization, and in particular, it's obtained as an infimum on the orthogonal L2 subspace to phi 1, right? So certainly lambda 2 is less or equal than Q evaluated on phi I over the L2 norm of phi 1 square, at least if you believe in the claim. And I hope you do so. So, well, I can just rearrange that stuff and sum over I. So I get the sum between 1 and 3 of L2 integral of fi square less or equal than sum over I of Q evaluated on fi. And now this stuff here, the stuff I have on the left-hand side, is certainly greater or equal than 0. There's no doubt about this. So let's try to now write down this term explicitly. So here I have, first of all, I have the energy terms. So I have the sum between 1 and 3 of the integral over sigma of grad sigma phi I squared. That's the first piece of the Jacobi operator. And then I have the algebraic terms. So that would be minus, and again, I'm taking the sum over I, integral over sigma. And here I can just apply the Shane-Yao rearrangement trick. So I will write it as 1/2 a square plus the scalar curvature of G fi square plus integral over sigma of k fi square. And that's it. Okay, so how do I treat the two terms? So let me observe here a couple of things. So the first thing that I want to observe is that trivially the sum between 1 and 3 of fi square is equal to 1. Okay, because these are coordinates of a point on a sphere, right? Remember that the outermost function here is just the I coordinate function. So if I sum the squares over I, I get 1. So in particular, I can take the sum inside these two integrals. And so this term here is going to be minus 1/2 integral over sigma of a square plus rg. Okay, because the sum over the fi is equal to 1. And here I get just the integral over sigma of k, so the Gauss curvature, but I'm working with the sphere, so I get 4 pi. And how about this guy here? Well, here I need to use a property that may have mentioned by Peter in class, I don't know, which is the conformal invariance of the Dirichlet energy. So this term here is conformal invariant, which means that I can just forget of these two maps in the composition because both of them are conformal. So phi is conformal because of the uniformization theorem, and capital F is conformal because I'm taking it in the conformal group of the two spheres. So this is just equal to the sum between 1 and 3 of the integral over S2, now with a round metric, of grad xi square. Okay, where xi is just the I coordinate function on the two spheres. And so, in particular, maybe let me go on the third board. So in particular, these integrals are just something I can compute with calculus. So I'm taking the two spheres, the I coordinate function, I'm taking the gradient, and I'm integrating. So I claim that each of these integrals equals 8 pi over 3. So what I get is that 0 is less or equal. So let's see. I have 3 Dirichlet terms. Each of them can be computed explicitly and equals 8 pi over 3. So I get 8 pi. So this is the energy term. Then I have these two terms here. So let me leave them implicit for 1 second. Okay, and then I have the Gauss-Bonnet term, which is 4 pi. Okay, so now I just take this term in the middle, I put it on the left-hand side, and keep in mind that Rg is greater or equal than 6. Okay, I will get that 6 over 2 is 3, so I get 3 times the area of sigma is less or equal than 8 pi plus 4 pi, which is 12 pi. Okay, and so the area of sigma is less or equal than 4 pi, which is what we wanted. So what is the moral of the story? Well, the moral of the story is that if we can do that conformal balancing, so if we can find an element in the conformal group that generates 3 evaluation functions that are orthogonal to the first eigenfunction, then this computation, which is fairly elementary, gives the area bound. So now let me try to convince you about why the claim is true. Right, so yeah, introduce the notation that lambda k's are just the eigenvalues of the Jacobi operator of the hypersurface in question. Okay, so how about the claim? So here is the reason why the claim is true. So, well, at least a sketch. So we have the conformal group of S2 times G0. Okay. Okay, that's associated to meromorphic function in C2, but that's not the perspective that I want to take. I just want to take the perspective that this group contains a subgroup which can be identified with the unit ball in R3. So roughly speaking, what I can do is that I can take a vector in the tree ball, and I can consider, this is of course quite sketchy, but I can consider the dilation on S2 of center minus V over length of V, which is a point on S2, and factor, and dilation factor 1 over 1 minus the length of B. And this is fine, so this is okay, at least if V is not the origin, okay? Because if V were the origin, then this quotient would have some problems. But then what I can do, so let's say that this dilation here is just denoted by FV. Okay, so FV will be a map from S2 to itself. And so what I can do now is that I can consider the map from B130 to B130 bar, so the closed ball, that does the following. I take a vector V, I construct the automorphism FV, and then I take the triple of integrals given by phi1 against xi evaluated on FV composed with phi for I equal to 1, 2, and 3. And what you can check, is that this map, which we may call capital omega, so capital omega has a C0 extension from the closed unit ball in dimension 3 to itself. So in particular, we can extend it to the boundary, and we can extend it to the origin. And I claim that actually in this continuous extension, omega, so in particular, what I claim is that omega restricted to the boundary of the ball in question will be pointwise equal to the identity. And so now you have a map from a ball to itself, which is equal to the identity on the boundary. So you use some basic algebraic topology or degree theory. And you get that there exists some element in the domain, so some V in the interior of the ball, such that omega at V is equal to 0. And such V is generating the automorphism FV that has this property that we wanted here. And so that's the proof of the claim, and therefore that's the proof of theorem 2. Okay, so now this is what we wanted to say about index equal to 1. So we have a nice existence theorem that says that, you know, if a certain topological assumption is satisfied, then we always have index 1 minimal surfaces. And so the next question is, how about higher index? So the next question is, how about higher index? And in general, this question is completely out of reach if you take even a three-manifold, which is general enough. So let me try to say something. So let's focus on the special case of the three-sphere with a round metric. So in this case, we have equators here. So this is index equal to 1. And so the question is, what is the next positive integer that is achieved, that is obtained as the index of a minimal surface in the three-sphere? Okay? And so we do know the answer to this question, and I claim that the next such integer is 5. And we actually do know precisely what elements achieve such value. So that's a famous theorem by Francisco Urbano, dating back to 1990. So it says that if you have sigma 2 minimal inside S3 with a round metric and non-equatorial, well then the index of such sigma is greater or equal than 5, and index equal to 5 implies that sigma is uniquely determined modulo isometries, so sigma is the Clifford torus. So what is the Clifford torus? Well, as a submanifold of S3, the Clifford torus is just the following object. So you take S1, so the one-dimensional, the circle of radius 1 over square root of 2, times, as a subset of R2, times S1 with the same radius. This is a subset of R4, but actually it's pretty obvious that it's a subset of S3, and you can check that it's in fact a minimal subset, a minimal submanifold. And one can pretty easily check that the index equals 5. In fact, it's a homework problem today. And Urbano says that that's the only guy having index equal to 5. So let me now sketch let me now give a sketch of the proof of Urbano's theorem. Before doing that, though, let me contextualize this result. So why is Urbano's theorem that important? Well, Urbano's theorem turned out to be crucial in the proof of the Wilmore conjecture. Okay, so I would like to connect this result with a couple of recent achievements. So the Wilmore conjecture was posed in 1965 and is now a theorem by Marquez and Neves. The proof was first presented on the archive in 2012. Okay, so the Wilmore conjecture basically says, well, asks what are the minimizer for the elastic energy of a torus in R3. Okay, so you want to minimize the Wilmore functional, which is the integral over the surface in question of the mean curvature square. And there's sort of a long story, but this problem turns out to be equivalent to another problem on the tree-sphere, which is the problem of determining the infimum of the area of sigma when sigma varies in the class M, which I'm going to define. So M is the class of sigma 2s in S3, which are minimal, embedded, but not spherical. Okay, so sigma 2 is not a sphere. Okay, so it's pretty clear that if you can prove the problem on the right, if you can solve the problem on the right hand side, then you can also solve the problem on the left hand side, because there's a stereographic projection that can transfer that you can use to transfer from one problem to the other. And so it turns out that the solution by Marquez and Neves is based on min-max, and in particular, it uses the characterization by Urbano. So it uses the fact that Clifford torus is uniquely determined by having index equal to 5. And there's a second result that I wanted to mention, which is the former Lawson conjecture, which is now a theorem by Simon Brendle, I guess also presented in 2012. So actually, the Lawson conjecture, which is a theorem, says that actually the Clifford torus is the only minimally embedded torus in S3 with a round metric. So not only torus is special in that it has a minimizing property for the area, but it's actually the only way of embedding a topological torus like a donut or the boundary of a donut in the tree-sphere. Okay, so and like I said, there's a strong connection between these three results, and it's one of the, I guess, one of the most exciting things that have happened in the last few years in the field to really understand this connection. So now let me say something about the proof of Urbano's theorem, which is the one that I stated here. So I mean, there's the inequality, which is fairly easy, and then remarkably enough, the equality case is again relying on the streak somehow in a different way from what we just did, but with a significant connection. So I find it interesting to present the two theorems in the same lecture. So, okay, so let's start. By proving the inequality, so index greater or equal than 5 unless you are equatorial. Okay, so then the proof of the inequality goes roughly like this. So there are natural candidate functions which come out of a computation which is by now pretty standard. So let's take, we have the three sphere in R4, so let's take E1 to E4, some global Euclidean basis in R4. Okay, so what we can do is that given sigma, it has a normal vector field n. Recall that three sphere is simply connected, so any minimal surface, well, any closed surface must be two-sided, so certainly we do have a normal vector field. And we can consider the following four functions. We can set fi, well, let's see. Maybe let me call them hi, yeah. Let's say hi is given by the dot product of n with ei. Okay, so these are two vectors in R4. Okay, I get a function in the following fashion. And there's a little computation which is made which is sort of described in the homework, which says that the Laplace operator on a minimal surface in the three sphere applied to hi is equal to minus the square of the second fundamental form of sigma times hi, which in particular implies, just by the definition of the Jacobi operator, that each hi is an eigenfunction with eigenvalue equal to -2. Okay, so now a remark here is that these functions, as I varies between 1 and 4, are linearly independent. So if I consider the space P given by the functions n dotted with v bar, where v bar is a given constant vector in R4, well, I claim that the real dimension of P is actually equal to 4 unless sigma 2 is an equatorial S2. So arguing by, it's pretty easy to see that if this space had dimension 3, well, then sigma should be contained in an hyperplane, okay? And as you slice a three sphere with hyperplanes, then the only way you can get a minimal surface is when the hyperplane passes through the origin and you get an equatorial sphere. Okay, so again, this is outlined in the homework. So in particular, if you take this remark together with this identity here, we have a nice four-dimensional vector. We have a four-dimensional vector space where the Jacobi form is negative definite with eigenvalue -2. But remember that the first eigenvalue must be simple. The first eigenvalue of an elliptic operator must be simple. Therefore, -2 cannot be a first eigenvalue, right? So here, if we try, so if this is the real line and we represent the eigenvalues of L sigma, we have here at level -2, we have an eigenvalue with multiplicity equal to 4. Then there must be something on the left. We don't know where, but we know for sure that there's something here with multiplicity equal to 1. So in particular, 0 is here. So you have at least 5 elements on the left of 0. So this says that the index of sigma must be greater or equal than 5. Okay, so now let me say something about the characterization of the Clifford torus as the only element for which equality is attained. Okay, so let's see. Okay, so now let's say that index of sigma is equal to 5. So this implies immediately that lambda 2, so the second eigenvalue, must be actually equal to minus 2, right? Because if I had something else apart from the red point, if I had something else here, okay, the index would be at least 6, right? So certainly this part of the spectrum must be like I drew it. Okay, so lambda 2 is equal to minus 2, and that's the information that we are going to use in applying the Hertz trick. So how does it work in this case? Well, okay, here we have sigma. We consider the embedding, which is actually the identity, but it's convenient to denote it with phi in the three-sphere with a round metric. Again, here we have an automorphism group, which is larger and more complicated than the one we discussed in the two-dimensional case. And on the other hand, we have the coordinate functions, which are just evaluations along the hypersurface, along the surface of the xi's. So the claim is that we can do conformal balancing, and the proof is similar to the one before. So there exists a V in, this time, the four-dimensional ball, such that the corresponding automorphism is balancing. That is to say, if I set Fi equal to the evaluation of the coordinate xi on Fv precomposed with phi, well, I get 4 functions, each of them being orthogonal to phi 1. Where again, phi 1 is a first eigenvalue. So again, phi 1 is a first eigenfunction for L sigma. Okay, so now we need to write down the functional inequality that we get, sort of explicitly. Okay, so we can use the Fi's as test functions for lambda 2. So we get at minus 2 times the integral over sigma of Fi square is less or equal than Q Fi Fi. Okay? But now, what is this guy here? Well, here I will have the energy term, and then I have the algebraic terms. But remember that the Ricci curvature of the Ricci curvature on the two-sphere is constantly equal to minus 2. Okay, so this guy, so I would have a minus 2 times Fi square, and then I have the second fundamental form term. So in particular, I have two guys that cancel out. So this guy will cancel out with this guy. So what I get is that the integral, okay, over sigma of a squared. Now I'm summing over I, so the sum over the fi's is equal to 1, as we explained before, is less or equal than the energy term. And here I have the sum over I. Okay, now I need an identity, which I'm not going to prove. I mean, it's fairly elementary, that says that twice the area of sigma, or phi of sigma, is equal to the sum between 1 and 4 of the energies, plus an extra term which is positive, so that's the integral over sigma of n against v squared divided by 1 plus phi v squared. So in particular, the Dirichlet energy, so observe that these two terms here depend on v. Okay, so v is the action of this, so v is the generator of the automorphism, so this term depends on v, this term depends on v, but the sum does not, okay? So this is independent of v. And so, in particular, I can certainly upper bound this energy term with twice the area of phi of sigma. Okay, now I combine this with Gauss-Bonnet. Now, we have already seen yesterday that actually the Gauss curvature of sigma is equal to 1, any sectional curvature of the sphere, minus a squared over 2, which I can rewrite as a squared equal to 2 minus 2k. So if I take this identity and integrate over sigma, I can find a lower bound for the integral over sigma of a squared. So in particular, using red box, I get that twice the area of f of phi of sigma minus twice the integral over sigma of k is less or equal than this piece here, which is again twice the integral of phi of sigma. And so this implies, right, these two terms are equal, so this implies that the integral over sigma of k has to be greater or equal than 0. So let's continue from there. So there are two cases. So now, by Gauss-Bonnet, there are two cases that are a priori possible. So the first case is when sigma is a sphere. So the first case would be integral over sigma of k equal to 4 pi, which is the same as saying that sigma is a two-sphere. But in this case, there's a theorem by Almgren, dating back to 1966, that says that the only minimal embeddings S2 in the round-tree sphere are equatorial. And in particular, if this were the case, then the index of sigma would be equal to 1. So we would find a contradiction, right? Because we are working in the index equal 5 case. As a result, the integral of k cannot be equal to 4 pi, so it must be equal to 0. And so sigma must be a 2 torus. Not necessarily the Clifford torus, that we still need to prove, but topologically it must be a 2 torus. Now, of course, if we were in 2017, which we are, I could use the theorem by Brendel and say that T2 must be the Clifford torus, right? Because now we do know that the only minimal torus in the tree sphere is the Clifford torus. But let's be honest, so let's go back to 1990, and so let's prove it, okay? In fact, the theorem by Brendel is a lot harder, so let's do an honest job. Okay, so the integral of the Gauss curvature is 0. But then, if this term is 0, then you get equality here, which means that if you go backward, you must have had equality at every single inequality that you had, right? And so I claim that in particular, this term here must, so if we are in the torus case, this term must be equal to 0 on sigma. Because if this term were not 0, then we would have a strict inequality somewhere, and therefore a strict inequality here. So in this case, you do backward tracking. And you get that for the balancing vector v, n against v must be identically equal to 0 on sigma. So now, how do you use this information? Well, now you set h equal to phi against v. So that's a function. It's just the dot product of the position vector of a point on the sphere against a fixed vector. Okay, so what you can do is that you can compute the Hessian, and that's again a standard computation and a classical one, and you get that the Hessian of this function is equal to minus the function itself times the metric restricted to sigma. Okay, so this is great news, because now whenever we have an Hessian equation like this, there's an important theorem in Riemannian geometry named after Obata, which we can apply. So Obata says, that's a theorem dating back to the 60s or 70s. Obata says that if h is not identically 0, then this identity is possible only if sigma is intrinsically isometric to a round to sphere. And the only minimally embedded round to spheres are equators, and again we find a contradiction. And so this is not possible. So h must be identically equal to 0. And so now there are two subcases that are both immediate to handle. So the first case is when v is not 0. So if v is not 0, then I'm saying that the position vector along sigma is always orthogonal to a given vector. So trivially, sigma must be contained in an hyperplane. So again, sigma must be an equator. Contradiction. So v must be 0. But saying that v is equal to 0 says that indeed we did not need any conformal balancing here. So this implies that fi's are nothing but the evaluations of xi on phi. No conformal balancing needed. Or if you want, fi is nothing but the dot product of phi with ei. And so now we also understand the Laplacian of those guys very well. So now the Laplacian over sigma of fi is equal to minus -2 times fi. And this is a general computation. But on the other hand, the backward tracking implies that if we go back to the first inequality we wrote there, I claim that we must also have at the same time that the Laplacian of fi must be equal to minus a squared fi. So I compare these two, and I get that a squared on sigma must be identically equal to 2. And then there's a theorem, also dating back to the 70s, due to Chern, Do Carmo, and Kobayashi, that says that the only minimal surface in S3 which satisfies this identity, so constant length of the second fundamental form, is the Clifford torus. which completes the proof. Okay, so that's all as far as Urbanus' theorem is concerned. So let me finish by trying to tell you how the story continues. So no proofs, just some ideas. So the question is, what is the next index? So what is the next integer that is obtained as the index of a closed minimal surface in the tree-sphere? So the question would be, what comes next? And the answer is that we don't know, but we do have very strong evidence. So we have strong evidence, and this is work by Charles Mercer, that indeed, after 1, which would be the equatorial spheres, and 5, which is the Clifford torus, the next integer would be 9. Okay? And this is, the evidence is based on what I would call computing higher width. And in general, we don't really know how that sequence continues. I would love to know it, but we don't. But we have some partial information that I should mention. And this is a theorem by Savo, dating back to 2010, which says that in a sense we can improve Urbanus' theorem, in the sense that we can bring the topology of sigma into play. So Savo proved that whenever we have a minimal surface sigma in the tree-sphere, its index is greater or equal than 4 plus the genus of sigma divided by 2, which in particular gives improved bounds compared to Urbano whenever the genus of sigma is greater or equal than 3. And so in fact, Savo proved the first special case of a well-known conjecture in our field, which is due to Shane, who phrased it in the 80s, and then Marquez and Neves, who posed it in a more general setting in their ICM lecture 2014. So the conjecture is that if you have a Riemannian manifold with Ricci positive, and you take, as usual, a closed minimal hypersurface, then it is expected that the index of any such hypersurface should grow at least linearly with the first Betti number. So there's some universal constant here times the first Betti number of sigma. And so notice that in ambient dimension up to 4, this is essentially only topological invariant. So this would say that somehow the topological complexity bounds from below the analytic complexity. And just to finish in the last 25 seconds, let me say that this conjecture up to 2010 was completely non-understood. Then Savo proved the spherical case in 2010. And now we don't have a proof of the whole conjecture, but we do understand it quite well. And in particular, let me close with the following theorem. So this is a theorem by myself, Lucas Ambrosio, who's now in Chicago, and Benjamin Sharp, who is in Warwick. So we prove the Shane conjecture in the following special case. Well, I don't quite have time to phrase it precisely, but the idea is that if Ricci is large enough, which is, of course, something that we can describe in a precise fashion. So we need to compare it with another tensor that comes into play. And the conjecture is true. And of course, this is a meaningless statement. Let me tell you that this Ricci large enough is satisfied pretty much in any example I can think of. In particular, the conjecture is true in the following cases. So all rank 1 symmetric spaces. Okay, so those would be spheres, RPN, complex projectives, quaternionic projectives, and the Cayley plane. Pinch tree manifolds. And product of spheres, for instance, together with perturbations. So the methods of Salvo seem to be very rigid and very tailor-made for the case of the sphere. Now we introduce a new perspective on the problem, which is intrinsically flexible, so that somehow we get an open condition that says when we can prove the conjecture for a given manifold, well, we can prove it in a neighborhood. Okay, and that's for instance enough to get generic metrics, which seem not to be within reach a few years ago. Okay, so I'm not sure whether we will ever see the proof of the general conjecture, but I hope there will be some progress very soon. Thank you very much.
So is this conjecture proved in dimension 3?
No. So in fact, Shane just posed it in dimension 3, and in that case, of course, the Betti number is equal to twice the genus. So that's precisely saying that we have a Savo type inequality without this additive term. Now the additive term is related to the symmetry of the tree sphere. In general, you don't expect to have the additive term, but still we do expect to have the genus term, and there's some heuristics behind this conjecture, which I don't quite have time to explain, but it's quite natural. So somehow the three-dimensional case is the most important case, but it's not clear to me that it's any simpler than the higher dimensional case. So in fact, I would expect that if we can prove the conjecture in dimension 3, then probably we would be able to prove it in any dimension. And our results, like the approach we introduced here, is completely independent of the dimension. So the technique doesn't really see dimension 3. Yeah, so that's not, well, first of all, I should say that evidence is not proof, right? So there's a famous statement by Gauss that, alpha, 1/2 of proof plus 1/2 of a proof equals 0 proofs in mathematics. So somehow this is the same story, right? So Charles Nurser computed the width, and the width what I would call the width spectrum is constant between level 5 and level 8, and equals 2 pi square. And then there's a jump at level 9. So if there's a justice in the universe, which means that if you do sweep out with 9 parameters, well, then you should get an index 9 guy. And if that were the case, and you get it without multiplicity, that says that you do indeed get that the third integer that is attained is 9, but we still don't know. Okay, so that being said, it is natural to expect that this should be the sigma 2, so the genus 2 Lawson surface. Okay, so this is what people expect. So there's a theorem by Lawson dating back to 1970 that says that for any genus greater or equal than 2, then we do have examples of minimal surface in the tree sphere with a round metric of genus G. And in particular, the examples, well, if the number is not prime, then there are non-isometric examples, which says that somehow the Lawson conjecture, well, you cannot expect the Lawson conjecture for higher genus. Okay, that being said, people believe that should be the genus to Lawson, but we don't know, and it may be very hard. I don't know. Well, yeah. So no. So the constant here is a function of the ambient manifold only, right? So of course, if you allow the constant to depend on sigma, then the conjecture is vacuously true. Oh, that's a good question. Actually, I think we only have an inequality. I don't think we actually know the index of the Lawson. I mean, certainly we have bounds. I think so. Yeah. I think that for sigma 2 it's equal to 9. Yes.
I was going to ask about the initial theorem.
Right.
There exists a closed manifold that does not contain hypotheticals with index. Though all minimal hypotheticals have index more than 1, especially more than 1.
No. So that theorem says, well, if you have this nice topological condition that you don't. Okay. Let me get to the point. So if there are no one-sided minimal hypersurface, then you have index 1. Well, you have index 0 or index 1 guys. That's what the theorem says. And if you have positivity condition, then the index must be at least 1, so equal to 1. Now, if that condition is not true, then in general, the min-max method could construct, and it will construct in certain cases, index 0 guys. So the point is not whether you jump from 0 to 2, but the point is that if you jump from 1 to 0, so if you go down. So somehow, the point is that when you start taking quotients, you could lose some index. So you have somehow index downstairs. Well, you have index, say, on S3, but you lose the index on RP3. That is somehow the phenomenon behind this. Okay.